Hello everyone, welcome back to alkaline hydroxide 784, and today in the chemistry series we'll finally be diving into the ominous topic of organic chemistry. I mean not on topic, the segment of chemistry called organic chemistry. Yes. So we'll be looking at the introduction today, so that's pretty much what it's called, the introduction to organic chemistry. And yeah, I say ominous because apparently a lot of people do not like organic chemistry and they prefer physical chemistry. But I, I, I seek to differ because I actually do like organic chemistry to some extent. And there are ways to make yourself like it. So, if you want to know how to like it, I can probably help you with that. But okay, as you can see in the syllabus, before you even look at the learning outcome, there's this bunch of stuff written above it. So we'll just go through that stuff very quickly because this is quite important when you go into organic chemistry. You need to understand what all of these things mean. So this is in regards to the different kinds of formula. So in the syllabus it says that they give the examples for plus like lactic acid and the different ways you can represent that lactic acid in terms of formula. Okay, so the first one is empirical formula, which is probably the most familiar term here, or one of the more familiar terms, because it's basically the simplest ratio as compared to the molecular formula. So you'd have probably tried to calculate this beforehand, like in previous topics. Yeah, like the very first topic maybe, and therefore this shouldn't be anything foreign to you. So for lactic acid, it is CH2O apparently. So there's twice the number of hydrogen atoms in lactic acid as compared to C and O. That's pretty much what you can get from here. But we do not know how many atoms specifically are there in lactic acid, and for that we need the molecular formula. And the molecular formula of lactic acid is C3H6 and O3. So it means we know that lactic acid has 3 carbons, 6 hydrogen, and 3 oxygen. But we don't really know how they're arranged. And we don't really you can't really get much out of it because there are other molecules that also have C3H6O3 as their molecular formula. So what makes lactic acid? Well, the structure of these particular atoms. And for that we look at the structural formula, which shows how the constituent atoms of the molecule are joined together. So like how the atoms are actually joined, but without really showing it in great detail. So what it does, in this scenario, they represent lactic acid as CH3, CH bracket OH, CO2H. So what this means is we know that there's a CH3 group at this end and a CO2H group at the other end, and next to the CH3 group there's a CH with the OH attached to the same C and then the CO2H. So that's what you can get from this. But even from this there is something that is missing, like you don't really know like maybe the arrangement of the bonds, or you don't know how it sticks out or sticks, like what's the 3D structure of the bond. So you'll look at that soon. So the next level of detail is the full structural or displayed formula. This will help you to clearly see the actual bonding, like whether single bond, double bond, and which atoms are bonded to which in this sense. So if you were to draw out the lactic acid in a displayed formula, this is what it will look like. Yeah, and from here you can actually see that there's a double bond between C and O. I mean, you can kind of tell if you know what CO2H means, but if you didn't know what it means, then you may not know how it's bonded in the sense. If you want to have this displayedness, but at the same time you don't want to write down all of the C's and the C's and the H's, you can go for something called skeletal formula, which will be quite prominent in organic chemistry because it saves you a lot of time. So this is a simplified representation of the displayed formula, and this is usually used in organic molecules, not really for other kinds of molecules. It's only in organic ones because usually the skeletal part is the carbons and the hydrogens. So there are two in the syllabus that been represented, a full skeletal and a partial skeletal. And for skeletal, we just don't write the C's. We represent it by the ends of the line or the joints between two lines. And the hatches are just assumed to be there based on how many bonds the C has. So like if the C is already bonded to one other thing, then the other three bonds are for the hatch. So there's three hatches. Or if you want to be a bit more clear about it, you can always do this. Write the partial skeletal formula and just write the H3C bond, like the so-called like an alkyl group at the end. But yeah, that's pretty much how it works. And for aromatic rings, you would usually draw a hexagon and draw a circle inside. That's how it's done in skeletal formula. And the final, most detailed one, I believe, is the stereochemical formula, which shows the 3D arrangement of the bonds. So in terms of space, like which one is sticking out, which one is sticking this side, you know what I mean. So in this scenario, the bolded ones, like the bolded lines, mean that it's sticking outside the paper, and the dashed lines mean that it's sticking inside the paper, kind of. And this is useful mostly for showing optical isomers and stuff like that. So chiral carbons and things like that. You can use this to show that, okay, these two are the stereoisomers. And yeah, that's for the structural, like that's for all the formulas that you can, the different kinds of formulas. And when you read them in the question, you must know what they mean. Yeah, you must know what you're supposed to give. If they ask you for a skeletal formula versus if they ask you for a molecular formula or a stereochemical formula or something, like you need to know what they're asking for. And you also need to know for certain kinds of questions like mechanisms what you're expected to give, whether it's a stereochemical formula or a normal displayed formula. So you need to be aware of this, which we will go through soon, I hope. Okay, so the next part is about the curly arrow notation, and this is for mechanisms usually. So what the arrows do is that we have the full arrow, which is just a normal arrow, I guess, to represent the movement of a pair of electrons from one species to another. And if you only want one electron moving, then you have a half arrow. So instead of drawing both the ends of it, you only draw one of it. Kind of like the reverse equation, that sign. Like imagine if you made that into a curvy arrow. Yeah, you get your half arrow. And yeah, that's pretty much how it works. Just need to know what this means. Yeah, so finally we'll get to the learning outcomes. The stuff I told until now isn't even the learning outcomes, just the stuff that you actually need to know before you do anything in organic chemistry, especially if it's A-level stuff. So yeah. Okay, so let's just follow through. So first learning outcome is to use the nomenclature general formulae and displayed formulae of the following classes of compounds. Okay, so for hydrocarbons, okay, so the first thing is hydrocarbons, which include alkanes, alkenes, and arenes. I do realize that the rest of the topics will be covering these things individually, like, for example, wait, where exactly is everything? Sorry. Yeah, so like the rest of the topics will be covering all of these separately, and we can look into them into more detail. So what I'm going to do now to save time is to not tell too much stuff about each of them. Just give a general description of what they are and maybe like just what they are. Okay, so alkanes are basically mostly just CH. Yeah, just C and H in a sense, and they don't have any double bonds. They're completely single bonds. So you would generally get a formula of like for example, you have methane, ethane, propane, so on and so forth. So that's alkane. And the general formula, like the empirical formula, would be yeah, so it will be CH2N plus 1. That is the general formula. So you have CH3, then you have C2H5, C3H7, so on and so forth. So that's how you define alkanes. Alkenes is basically alkanes with at least one double bond. Okay, but if you're looking at single double bonded alkenes, you will generally get an empirical formula of C. Oh yeah, sorry. For alkanes, it's CnH2n plus 1, right? So alkenes, it is CnH2n. And if you keep increasing the number of double bonds, you keep minusing the number of n's by 2. It's pretty simple. And for arenes, yeah, arenes are basically the, well, yeah, like the aromatic things, aromatic stuff. So those are arenes. And if they're fully CH, then they're just simply hydrocarbon. Nothing much to say about it. If you want to know what's a triple bonded thing, that is alkyne. Yeah, that's triple bonded. It's alkyne. Okay, so the next one is halogen derivatives. And for halogen derivatives, we have halogenoalkanes and halogenoarenes. So alkanes, I mean, you already know what an alkane is. So what happens here is, instead of everything being hatched, one of them, at least one of them, is replaced by a halogen. That will be like Cl, I, or Br, mostly those three. I think F might come, but it's usually Cli or Br. And for halogenoarenes, it will be an aromatic compound, but one of them. Wait, sorry, not aromatic. Is it aromatic? What am I saying? Yeah, it's aromatic, like benzene, that kind of stuff. That's arene. Okay, so aromatic compounds where one of the hydrogens is, at least one of the hydrogens is replaced by a halogen. That's basically halogen derivatives. Then the third one is hydroxyl compounds, and now this time instead of halogens we have OH in a sense, but they have a special name, which is alcohols if you're looking at alkanes, or alkene, and phenols if you're looking at arenes. So yeah, that's pretty much it. So alcohols will be something like ethanol, methanol. So in like one of the N's will become an OH, like one of the H will become an OH instead. And for phenol, it's basically just a benzene with one OH group. Yeah. And then the next one is the carbonyl compounds, which involves the carbonyl group. And the carbonyl group is basically the C double bond O group. It is different from carboxylic group, but so a carbonyl group is C double bond O, and you can find this in aldehydes and ketones, and they are both basically alkanes with the carbonyl group on it. So the difference between the two is that in the aldehyde, the carbonyl group is at the end, versus for the ketone it is in the middle somewhere. So there's a difference between how they get oxidized, and we'll find out more about it in their actual topic. And I'm not going to talk about it right now. Yeah, you have to wait for that episode to come, I guess. Okay, so the next one is carboxylic acid, and carboxyl group, as you all know, is COOH. The carboxyl kind of comes from hydroxyl plus carbonyl, I believe. It kind of makes sense to me. So it's like CO plus OH becomes COOH. That kind of makes a lot of sense. So that's how you remember what it is. So carboxyl groups. So it's carboxylic acids and derivatives. So that's the whole group name. So carboxylic acid is basically just acidic compounds, I suppose, with using a carboxylic group at the end. So yeah, like lactic acid has a carboxyl group at the end, as we saw earlier, so the COOH. And if you're looking at the carboxylic derivatives, instead of simply just a carboxyl group, the OH, so you can look at acyl chlorides and esters. So for acyl chlorides, you have the COO, not OH, but Cl. So you have COOCl, sorry, not COO, COCl. Yeah, something like that. because Cl is -1. Yeah, you can just, so it replaces the OH in the carboxyl group and it becomes an acyl chloride. And for esters, they're basically the carboxylic acid plus the alcohol, that thing, you know that, but you know what happens there, like the condensation reaction. And the final one is nitrogen compounds, which involves nitrogen. That's the easiest way to look at it. And they have a lot of stuff. There's amines, there's amides, there's amino acids, and there's nitriles. So, amines would have, I think, NH2 groups. Amides, I think, as I don't remember. Wait, let me just quickly scroll down, because it will be there, right? Okay. So, yeah, amines are just NH2 groups, I guess. Amides are like acyl chlorides, but it's like CONH2, that kind of thing. Yeah, it's something to do with that. And then amino acids are bio stuff, so yeah, it's easier to explain it in the actual topic. And nitriles are the C triple bond N, I believe. That's nitriles. Okay, so let's just move on. Okay, so the next learning outcome is interpret and use the following terminology. Okay, so the first one is functional group. So what's a functional group? We saw all these examples, like all the different possible stuff that we can look at just now, and the functional group would be something like the OH or the carboxylic group or whatever group that is not the H in a sense. So that's what a functional group is. It's like the group, you can kind of substitute the H for this group. That's basically what it is. I mean, technically a methyl can be a functional group too. But yeah. Yeah, so that's basically what the functional group is. Like that, if you read it, that's what you understand it to be. You don't really need to write the definition of functional group, so please don't write this. Okay, so next one is degree of substitution, which, well, yeah, that's pretty simple to say. We have 4 degrees, which is primary, secondary, tertiary, and quaternary. The reason why is because a C has 4 bonds. So like if we start off with a so-called CH4. Wait, did I miss? Oh wait, methane is CH4. Sorry, I said it wrongly just now. Yeah, for alkanes it's actually like CnH2n plus 2. So alkene would be CnH2n. Yeah, sorry. Okay. Never mind about that. So for C, we have 4 different bonds. So if we start with CH4, for example, a primary substitution will be one of the H's becoming something else. Like you replace the H with a Cl, maybe not a Cl, you wouldn't replace it with a Cl, with something else basically, I don't know. I mean, technically you can replace it with a Cl, but okay, fine. Let's just say you replace it with a Cl. Then a secondary substitution would be if you replace 2 of them. And tertiary would be if you replace 3 of them, and quaternary would be if you replace all 4 of the H's and there's no longer any H's on the C. That's basically the degree of substitution. So it shouldn't be that hard to figure that out. Okay, so the next one is homolytic and heterolytic fission. Homolytic and heterolytic fission. Okay, so fission basically means you break the bond. That's the first thing to take note of. The bond is being broken. So homolytic means that the 2 electrons, the electron pair, goes to only one of the species. But heterolytic means that the electron pair will split up and each of them will go to one of these things. And I can represent that with the arrows, and that's why we need to know what they mean. Yeah, that's pretty much what it means. Okay. So usually if you have like homolytic fission and you did it on a Cl2 molecule, you end up with one Cl, like full Cl minus kind of thing, and you have one that's Cl plus. But that doesn't usually happen, so Cl2 usually undergoes heterolytic fission, and one electron will go to each Cl and it becomes two Cl radicals. Yeah, yeah, you'll find out more about that later. Okay, so next one is carbocation, and basically a carbocation isn't like a normal cation, but it is more like a positive, like electron poor carbon basically. So the carbon is surrounded by things that pull the electrons away from the carbon, and therefore it behaves a bit like a cation, even though it isn't really a cation in a way, and therefore it kind of attracts electrons to come and, you know, come into that area and do some, like, break the bond or something. I don't know. Yeah, like basically bond to the carbon and then get rid of whatever's already bonding to the carbon. Okay, so the next one is free radical. Oh yes, I literally mentioned it like 30 seconds ago. So the chlorine with like like basically the chlorine but without the minus on it. So it has to have 7 electrons and it's alone, and basically has like this unpaired electron there, and it's a radical. Basically that's what a radical is. It has an unpaired electron. So that's a free radical. Initiation would be, oh, initiation, propagation, termination. Okay, these are like the steps in the mechanisms. So if in terms of this, we have to look more about this in the, you know, the topic where I can actually cover them in greater detail. But this is actually referring to usually the free radical substitution, and initiation is when the chlorine kind of breaks up into two radicals. The propagation is where the radical makes other things become radicals while creating the products as well. And the termination is when two radicals come together and then it stops making things radical. That's basically the idea, and the whole thing finishes at that point. Okay, that's how it works. Okay, cool. So the next one is electrophile and nucleophile. So if you remember what the definition of a Lewis acid is basically just an electrophile, and a Lewis base is a nucleophile. So an electrophile likes to, you know, sorry. Okay, so the electrophile is the one that is kind of positive, and or at least it wants electrons, and the nucleophile is the one that wants the like the nucleus kind of thing. So that's how you interpret the name. That's how you figure out which is which. So the electrophile wants electrons because it is electron poor. So it wants it like electron pair acceptor in a sense, and the nucleophile wants a nucleus to give the electrons to, because so it likes the nucleus instead, and it's an electron pair donor. Actually, this is a good way to remember which is which, I guess. I don't know. If you prefer thinking about it like that, you can just do that. Okay, that's what it is. Okay, so next one is addition, substitution, elimination, condensation, hydrolysis. Oh wow. Okay. Addition is basically if you add one thing to another thing, kind of. I have no idea what just happened there. Okay, so like you have two molecules and you add one to the other. That's addition. Substitution is if you substituted the H for a Cl. That's basically substitution, or for any other group. Elimination would be also, oh yeah, for addition you might be wondering how you're going to be adding things together. Usually you can do it if you have a double bond. So if you add something, you can break the double bond and then create more bonds. That's how you can add stuff. Yeah, that's just an extra note. Okay, so for elimination, you're removing something and remaking the double bond, kind of. Condensation would be a reaction that creates a water molecule. So usually the esterification reaction would create a water molecule. I mean, it could also be an yeah, usually it's that kind of reaction. Like two things coming together. When they come together, you get water molecule out of it. That's what is eliminated from the whole thing. Yeah, elimination can also be kind of like elimination is like the bigger like bigger set and condensation is like a subset. So elimination can be also for stuff like HCl or other things. So we will look at that in the various topics. And finally hydrolysis, which is adding the water back in and then breaking it, and then breaking up something using water. Basically that's hydrolysis. So because it basically comes from hydro, which is like water, and lysis, which is cutting something. So yeah, that's hydrolysis. Okay, so the final one is oxidation and reduction. Yes, I think we all very clearly know what these two terms mean. Oxidation means like if you have the oxidation number, you can use, I think that's the best way to describe it, because if you use purely O and H, it may not describe all of the reactions that could be oxidation or reduction. So, but we'll start with the simple definition first. Oxidation would be adding oxygen, removing hydrogen, or an increase in the oxidation number. Likewise, reduction would be removing oxygen, adding hydrogen, or reducing the oxidation number. Yeah. And a quick note on how to calculate the oxidation number. Well, basically, if let's say you have a molecule, let's say you start with the C. If the thing that is bonded to is less, electronegative to it, then you would say that you'll say that thing is +1, and then the C becomes -1. So imagine like the H is like a H plus cation that attached to the C, like the carbon atom. So the carbon gets a -1 if there's a H attached to it. But if there's an O attached to the carbon, the O is a electronegative atom. So if it's just an O, like C double bond O, then you would be plussing 2 to the C because O is -2. But if it's a OH, then you only have to do 1. So if let's say you have like maybe ethanol or maybe methanol, so it's CH3OH. So what is the oxidation number of C? It would be, well, there's 3 H's, so C will become -3, and there's 1 OH minus, and therefore you add 1 back. So the oxidation number of C is actually -2. Yeah. So from there you can calculate the oxidation number when you are not sure what it is. But if you have the charge of the atom, usually that is the oxidation number. So like Fe2 plus, Fe3 plus, you get the oxidation number from looking at the charge itself. Yeah. Okay, so let's move on. The next learning outcome is interpret and use the following terminology associated with organic reactivities. So the first one is delocalization. So delocalization basically means that the electrons are no longer staying in place. Basically, they don't stay within the bond, they move all around the place. And this would be most visible in a benzene ring, because the electrons, there's only like 3, like there's only like 3 ways. If you see the skeletal formula, that you know it's not really just any plain double bond or something. It's like in between a single bond and a double bond. So the extra electrons are kind of delocalized, and they don't really stay in place, and they can move all around the place. And therefore, even if you were to draw the hexagon with 3 double bonds, it's not really reflective of the actual reality of what's going on there, because the electrons can move everywhere, and the double bond can change from this way to that way, and this way and that way, and we don't really know where exactly the double bond is. It's more like it's just over the entire 6 carbon atoms, and it will work with other double bonded things as well. And this is because in double bonded atoms or triple bonded atoms, we have hybridization, and that would, so not hybridization, we have unhybridized p orbitals, and therefore those p orbitals can actually do the whole delocalization stuff basically. So the next one is electronic effect. So electron donating, electron withdrawing effect. Basically electronic, what this means is in a benzene ring, if you have a thing attached to it, like ClO, something like that, different things attached to it will have a different effect. So some of them are very electronegative, and they like to withdraw electrons from the benzene, or some of them on the other hand are not very in need of electrons, and therefore they don't they give electrons instead. So there's a difference between electron donating and electron withdrawing. So if the group is electron donating, it will push electrons back into the ring and make the ring more negative. If it's electron withdrawing, it will pull electrons away from the ring and make it more positive and make it more susceptible to attack by a nucleophile, I suppose. Yeah. Then the final one is steric effect, so steric hindrance. Basically, steric effect is basically like space. Like imagine just a space, and you're in that room, in a room with it's completely empty, so you can move everywhere. But now you move to another room, and that room has like 10 different pieces of furniture there, and they're all over the place, and you can't move. Basically, they pose some sort of a steric hindrance because they're big, and you have lesser space to move around or to do anything much in the room. Likewise, around a molecule, if there's a lot of things around it, like big bulky stuff, like let's say you compare a methyl group as compared to just a small little hydrogen, it's a bit harder for things to come and attack the C there. So that's steric hindrance. That's the idea of the steric effect. We will look at that in the various topics as well. So the next one is describing the different kinds of hybridization and relating them to different molecules as mentioned in the syllabus here. Okay, so sp3 hybridization as in ethane molecules. So sp3 hybridization is, as you can see, is fully like single bonds in a sense, and therefore like each of the like the s orbital and the p orbitals all kind of hybridize, and p orbitals, there's three of them, right? So they all hybridize with the s because there are four regions of electron bonding in the sense. So they all hybridize, and then they can form like four equivalent orbitals, which can be used for the so-called tetravalent bonding, as carbon is most well known for. And this will give that tetrahedral kind of shape in a sense. The steric shape will be somewhat tetrahedral. So ethane molecule will have a tetrahedral orientation around it, and the angles will be 109.5 degrees, kind of. So the next one is sp2 hybridization, as in ethene and benzene. sp2 hybridization is when one of the p orbitals is not hybridized with the other two p orbitals and the s. So there's one free p orbital, as you can see in ethene and in benzene, and this is because the p orbital is used for double bonding. So if there's a double bond, it will no longer be sp3 hybridization, so just make sure to take note of that. So in sp3 hybridization, only three hybrid orbitals are formed, and those three are in the same plane, and the last p orbital will be like in a perpendicular axis to them. Imagine it like the z axis, and then the other two are in the xy plane, kind of. Yeah. And therefore this particular p orbital that's sticking out on both sides is the one that can create the delocalization by making a pi bond with the other p orbital in the other molecule, and creating like this region of free space for the electrons to move. Okay, so ethene and benzene will both have this. Benzene is very special because there's like 6 atoms all having sp2 hybridization, and then this creates like a full ring of linked p orbitals on the top and bottom. Like they're the same thing, but that it's like one single region of electron space, but it's split over the two halves of the benzene ring, I guess. I don't really know how to describe it, but you get the idea. So electrons can move throughout that entire space. And the angle is 120 degrees because it's like, imagine you have like a pie chart with only 3 segments in it, kind of like a Y shape. trigonal planar. If yeah, kind of. I think so. Okay. And finally, we have sp hybridization. And I was talking about alkynes. Yeah, this example is an ethyne molecule, which has a triple bond in it. And the triple bond means that only one p orbital will hybridize with the s, and that forms two, um, you know, things like two hybrid orbitals for single bonding. And the other two p orbitals are used for triple bonding. So it will form like one this way and one that way. Hopefully I can draw it nicely. If I can, then I'm sorry. Yeah. Okay, so the next one is explaining the shapes and bond angles in these things. So for ethyne, it is actually 180 because there's only there's only wait, what am I thinking? There's only two regions, I guess, kind of. So like sp3 has four regions, so it's tetrahedral. sp2 is three regions, so it's kind of, yeah, so it's basically two. Yeah, so I need some time to think of what exactly I was trying to say. So like in a CH4 you have the four regions, right? Then if you imagine it's CH3, there's only three of them attached, and sorry, there's only two of them attached, and the last one is a double bond. It's sp2 hybridization, and there's only one attached, and the last one is a triple bond. You get sp hybridization. Okay, so I'm gonna explain it in a bit more clearly with sigma and pi bonds. So for ethyne, it is actually 180 degrees, the angle. Okay, it's just linear orientation, the shape, I suppose. Okay. So the sigma bond is for the single bond. It's the first bond, and it's present in all of the three kinds of bond: the single, double, triple bond. They will all have a sigma bond. So it's the first and foremost bond that is formed. And so if you were to imagine something like sp2 hybridization, so we're going to look at double bonding. So we first imagine like two single bonds forming with hydrogen, and the last hybrid orbital forms the so-called first bond of the double bond, which is a sigma bond. Okay, and then the pi bond is formed between the p orbitals exclusively, so not between hybrid orbitals, but between pure p orbitals or d orbitals maybe. So in this scenario, it is added on to the sigma bond that's already there. That's why you still have only that number, that many bonds and total, that many regions of bonding. So that's how a sigma and a pi bond works. And because of this, usually the pi bond is slightly weaker than the sigma bond due to the side-on overlap rather than a head-on overlap. And this means that the double bond energy is not twice that of the single bond energy, and neither is a triple bond energy twice that of a double bond of a single bond energy. Yeah. So yeah, now that I told you the shapes and the angles and stuff like that for each of these three, you just need to relate it back, like how we have the VSPER theory. Like, so you use the same logic and apply it for other molecules that look like this and predict the right angle and things like that. So if it's tetrahedral, you get like 4 bond tetrahedral, 109.5. There's 3 bonds, it's 120 degrees. It's trigonal planar. Is it trigonal planar? I don't remember what the names of everything. Oh no. But yeah. And then if it's 2 bonds, it's just linear and it's 180. Yeah, that's pretty much it. The next one is apply B and C to understanding of mechanisms in terms of organic structure and bonding. What is B and C? Oh, okay. The terminology. I mean, I don't really want to extend this longer than it already is right now. So what I will tell you is how you use it. Basically, mechanisms will have a lot of steps to it. Like there's like steps to it. There is stuff that you explain from the mechanism, and from there you had to use these terminology like the functional groups that are swapped toward electrophile, nucleophile especially, and the free radical part. Definitely there's a free radical substitution, and also the whole idea of the delocalization, electronic effect, steric effect, because these things have a role to play in the susceptibility of one atom versus another atom to a specific reaction. And this we will look at in greater detail in the topics, so hopefully, yeah. But for an example, maybe we say steric effect. If the molecule has steric hindrance, it's less likely to get attacked by something because there's no space. Or you could say that the steric hindrance on one side of the molecule makes it such that the attacking molecule attacks it from the other side. So that kind of determines certain aspects of the reaction. For example, the stereochemistry of the product, for that matter, or other things that, like the rate of reaction and things like that. So yeah, that's pretty much how you would explain using terms like that. But we'll look at it in the other topics. So the final learning outcome, yes, finally, is to recognize that the mechanisms of polar reactions involve the flow of electrons from electron-rich to electron-poor sites. Polar reactions, so in a polar molecule, you obviously have this one side which is very electron-rich and one side which is very electron-poor. And therefore, the electron-rich side will kind of act like a nucleophile and will want to attack something that is like a carbocation or something of that sort. So that actually is pretty much how you understand the mechanism of polar reactions. And therefore, these electrons want to go to somewhere which is electron-poor again. So that's the reason why the reaction even happens. That's pretty much it. Okay. So yeah, we're done. Yay. So I hope you found this video useful, especially the first part where I explain all the formula and stuff like that. And I'm sorry that the video is quite long, but I expected it anyway because look at the number of stuff I had to cover. So yeah, it's kind of hard not to make this not long. Yeah, it's not like solubility equilibria, which is like literally 3 learning outcomes. This is what, until it has not just the learning outcome but the stuff before the learning outcome. So you know what I mean. Yeah. So I hope you found this video useful, or at least found it enjoyable. So if you did, please press the like button and subscribe. And with that, I would like to say thank you and bye.